So combinations of functions and composite functions. We are going to take individual functions today and, like it says, combine them and compose them. I, again, find this really fun, so even if you hate it, you have to pretend that you like it with me. Before we really get started on combining functions and composing them, we need to talk about the domains of particular functions. Wow, I thought I heard somebody at the door, but that was not. So the domain of a function, for all functions except for four, really three, add four cases, the domain of all functions is going to be all real numbers. That's a pretty easy answer. So a quadratic, all real numbers. A linear, all real numbers. The only kinds of functions that do not have a domain of all real numbers are the following. Number one, functions that model data or provide verbal conditions. So like, let's say we have a word problem and it says that you're selling shoes or you're counting time. You can't buy negative shoes and you can't time travel. So we have to make sure in context of a real problem, we're not using negative numbers for time. We don't time travel in this class. Or you're trying to sell negative ice cream cones or negative shoes. That doesn't make sense. It's a real life thing. The second type of function that's going to have what's called a restriction on its domain is a rational function. When an x is in the denominator, you know you cannot divide by 0. So we have to set that denominator not equal to 0. That is one of the domain restrictions we're going to use. In fact, I'm going to use a different color for this. Sorry if you're following my color scheme. We're going to use red, pink, whatever. So the denominator cannot equal 0. The second type of function that has a restriction, meaning not all real numbers for its domain, is the square root function. For the square root function, because you cannot take the square root of a negative number, you're going to have to take that radicand, which is the stuff underneath the square root, and set it greater than or equal to 0. The last type of function that has a restriction on its domain is a logarithmic function. We're not really discussing logarithmic functions in details. That's what chapter 4 is about. But just know as a preview, logarithms will also have a restriction on the domain. The argument has to be greater than 0, but we will discuss that later. We're focusing mainly on these two today, rational functions and square root functions. So one of the questions you'll have is, what is the domain of the function? You always start by figuring out what type of function it is. For letter A, f of x equal to x squared minus 7x, what kind of function is that? It's squared, which means it is even. Okay, could potentially be even, is even degreed. It starts with a Q is what I'm looking for. It's a quadratic, yeah. This is a quadratic function. A quadratic function, no matter what, has a domain of all real numbers. So we'd say it goes from negative infinity to positive infinity. Boom, done. No work needed because a quadratic has no restriction on its domain. What kind of function is this second function? It starts with an R. A rational function or a reciprocal function. In a rational function, the denominator cannot be equal to 0. So if we're finding the domain, there is a little bit of work here. We're going to take that denominator, which is x squared minus 2x minus 3, and we're going to say that cannot be equal to 0. So it's equals with a slash through it for not equal. Well, that means I'm solving a quadratic for what it's not equal to. When we solved quadratics, we factored, which this would become x minus 3, x plus 1, not equal to 0. Which means there are two numbers that x cannot be equal to. What are the two numbers? Let's see, it's too loud. Say it again. One of those is negative. Which one? It's actually 3 and then negative 1. Remember, you change the signs when you're solving for x. So that means I have two numbers that my function is not allowed to be equal to. Those are the restrictions on my domain. To write this in interval notation, you may need a number line to make this make sense. So right now, these are our notes. If eventually you can see it without the number line, that's totally fine. Here's the number -1. Here's the number 3. We just can't be these numbers, but we can include every other part of this number line in my domain. Just not number -1 and not 3. So to write this in interval notation, I would say the parts that I shaded in started at negative infinity, went to -1, went from -1 to 3, and went from 3 to positive infinity. There's 3 little breaks in my graph, 3 intervals, so I have 3 intervals in interval notation. Whoa, a lot just happened really quickly. Let's backtrack and make sure we understand. We started with a rational function. Rational functions, the denominators cannot be equal to 0. So we need to figure out what numbers would make that 0. We say the entire denominator not equal to 0. We solved like it was a regular quadratic. It's just these are the numbers it's not equal to. Put those numbers on my number line and pluck them out of my domain. We have 1, 2, 3 intervals. So I have 1, 2, 3 intervals. Questions? For number C, what kind of function is that? A square root. A square root function does have a restriction on its domain. The restriction is that that stuff I've highlighted in blue called the radicand has to be greater than or equal to 0. So that's how I start. I'm going to say, all right, 3x plus 12 has to be greater than or equal to 0. This is a small little linear function that I need to solve. I would subtract 12 from both sides. I would divide by 3. So I know that I need all of my x values that I plug in to be greater than or equal to -4. You might be able to go straight from inequality notation to interval, but if not, I always find it helpful to draw a number line. Here's the number -4 on my number line, and I'm going to put a closed circle on -4. Why is it closed as opposed to open? Because it's equal to. The or equal to part closes that. Now, where are numbers greater than -4? Are they greater on the left side or on the right side? Right side. So I'm going to color in, I'm going to shade in on the right side of my number line. And that shows me on a number line the interval how I want to answer for this domain. This domain is from -4 with a bracket all the way to infinity with what? Infinity with the parentheses. You're welcome. Okay, we follow, yes? How about this third one? Fourth one. For j of x, what kind of function is that? First thing I notice is that we have a fraction, so here's a denominator, but what is inside the denominator? We're going to have to do 2 things, okay? We're going to have to take care of the red, we're going to have to take care of the blue, we have to do both, okay? Doesn't matter which one you do first because we're going to put all of the work on the same number line. So I'm going to say that the pink stuff for me is square root of 14 minus 2x cannot equal to 0, and that 14 minus 2x has to be greater than or equal to 0. Those are the 2 restrictions for the fact that it's a reciprocal function, rational function, same thing, and a square root function. We solve both. To solve the pink thing, I'm going to square both sides, and I have 14 minus 2x cannot be equal to 0 squared, which is 0. Subtract 14 from both sides, so -2 cannot equal -14. And then x cannot equal to 7. Okay, I know there's going to be a hole on my number line at 7. But we also need to solve the blue side. So I'm going to subtract 14 from both sides. I'm going to divide by -2, and hopefully your spidey senses are going off. When you divide by a negative number with an inequality, what do you have to do? Flip the sign. Okay, good. We remembered that. So now I need to combine both of these inequalities onto one number line. Things occur for this guy at 7. Now 7 has an open circle because of the pink, because it cannot be equal to 7. And then I need all of the numbers to be less than or equal to 7. So I'm going to color in on the left side. So even though this one tells me I should be able to be equal to 7, can I actually be equal to 7? No. If it says not equal to a number, you have to take it out, even if the other one says it should be. This one wins. So if we were writing this as an wow, I just forgot the word. Thank you, interval. This would be -infinity to 7. It feels like such a Friday in my brain right now. Oh my goodness. Okay. How do we feel about finding domains? For functions that are not a radical, oh my gosh, rational or a square root or eventually a logarithm, this is the answer every time. All real numbers. But if you have one of those types of functions, you have to give me a restriction on the domain. Now we're starting with this. We haven't combined or composed functions at all because we have to think about the domain when we do combinations and compositions. So this is always going to be something we're going to start each problem with. We have to check to make sure the domain of the function has no restrictions before we start combining it in different ways. Because when we go in to do algebra or combinations of functions, we have to make sure that the domain exists for both cases. So all of these words are here to say the domain for each of these functions that you're composing, adding, subtracting, multiplying, dividing, it's combining, not composing, must be common to the domains of both f and g, meaning the domain of your combined function is the intersection of the domain of f and the domain of g. Kind of the same way we combined our domains in this guy over here, where there was two restrictions at once and we combined them together, that's what we're going to have to do when we do algebra with functions. Can we see what this looks like in an example? So the first thing we're going to do with functions is we're going to combine them. You can add, subtract, multiply, and divide functions from each other just like you can regular numbers. You have the sum if they're added together, the difference if they're subtracted, the product if they're shoved next to each other, that means multiply, and the quotient when they're divided. These domains are the set of all real numbers common to domains of f and g. So we're looking at the intersection. For a lot of these, this is very simple. The ones that we're going to have to pause on are going to be the product and the quotient if you're looking at either of these two. These are going to be the ones that give us pause. But let's look at okay, so we're going to combine these two functions together. So this whole time that I'm working, I'm going to let function f be green, and I'm going to let function g be purple. I just find it easier to color code stuff when we're combining and composing because you'll start to see where things come from. Before you start any problems today for combining or composing, always check the restrictions of the original domains. What kind of function is this green one? Linear. What kind of function is the purple one? Quadratic. Are there any restrictions for linear or quadratic? No. So the domain of the green function is from negative infinity to infinity, and the domain of the purple function is also all real numbers from negative infinity to infinity. So we have no original restrictions for these problems. You always want to start by checking the domain of the original functions. Because when we start to combine them, and like let's say we do f plus g, that means we are going to take the two functions and we are going to add them together. So we're going to take the green function and we are going to add the purple function. For adding, the parentheses seem extra, but I promise if you always start with putting things in parentheses, eventually you won't make mistakes when that's absolutely needed. Yeah. So if we start to combine these, yeah, the parentheses are extra because nothing changes sign here. So we're going to combine like terms. How many x squareds do I have? Just one. How many regular x's do I have? 3. And how many constants do I have? Negative 3. This is f plus g. We have combined them together. The original functions were all real numbers and all real numbers. What kind of function did we create when we finished? Is there any restriction to a quadratic? No. So the domain of this function is still going to be all real numbers. We didn't create any problems when we did this because all we did was add them together, combining the function. If we do a little bit more algebra with this function, so let's this time do f minus g. So we're going to take the green function, 2x minus 1, and we're going to subtract the purple function, x squared plus x minus 2. This is especially important when the negative comes into play for the parentheses, which is why you should do it every time, just so we don't forget. Since we have a negative, we're going to distribute that negative or change the signs of everything inside that parentheses. So my work step would be 2x minus 1 minus x squared minus x plus 2. Change all those signs. Combine like terms. Starting with the highest degree, we'd have negative x squared and then positive 1x and then positive 1. Just combining our like terms. So this is f minus g. We're just subtracting the two functions from each other. You made it. That's okay. All right, what kind of function did we create here? Quadratic. Is there any restriction to a quadratic? No. So its domain is still all real numbers. This feels repetitive. It feels like nothing's happening, but times it will happen. So we always want to check. If we do the product, so we're finding the product now. This is going to be f times g. Again, we're going to use parentheses. We're going to do 2x minus 1 multiplied by x squared plus x minus 2. This is like a FOIL question, but more aggressive, because now we're going to double distribute to three things. So it's a binomial times a trinomial. We're going to distribute carefully. Boom, boom, boom. We distribute. My first step would be this becomes 2x cubed plus 2x squared minus 4x. Did I lose anybody? And then if I distribute the bottom, the second term, it's like an aggressive FOIL, right? Lots of foiling happening here, lots of distributing. We end up with negative x squared minus x plus 2. Then we have our cleanup step, because we have a couple like terms all separated, so we're going to write it in standard form. This would be 2x cubed plus 1x squared minus 5x plus 2. What kind of function was created? Cubic. Does cubic have restrictions? No. The only ones that have restrictions, remember, are rational, square root, and eventually logarithms. What time is lunch today? 15, right? Yeah. Okay. Sorry, I'm hungry. Okay. Pause for a second. We have done addition, subtraction, and found the product, multiplication. Are there any questions so far? When we get into the quotient, meaning we're doing dividing, this is one that you know for sure we're going to have to pause on because we are creating a rational function. If we do the quotient, f divided by g, it tells me to put f on top. So here's 2x, I already forgot the function, minus 1. And x squared plus x minus 2 on the bottom. What kind of function have I just created? This is a rational function. Hopefully your spidey senses are going off, because when we had rational functions, what did we have to do with the stuff in the denominator? Not equal to 0. So I'm going to have to take this stuff that I just put in the denominator and make sure that I don't make it equal to 0. I have to provide that restriction. Okay, I've got a quadratic not equal to 0. How do I solve a quadratic? Factor it. Walk me through factoring. What should I put in the front of these parentheses? Both get an x. And I ask myself what question? Yes, so what multiplies to negative 2 and adds to positive 1? So it should actually be plus 2 minus 1. So what are the two numbers that x is not allowed to be equal to? -2, and +1. So that means for this function, for the f divided by g, the domain is no longer all real numbers. Even though we started there, when we combined them, this domain becomes -infinity to -2, -2 to 1, and 1 to infinity, or 1 to infinity. Because we created a problem by putting a function in the denominator. If you're like, Ms. Quigley, where did these intervals come from? I skipped the step by showing a number line, so you might want to see the number line there. But those would be your 3 intervals on the number line. Does that make sense? If you create a problem, the way you combine them, you have to fix the problem and tell me about the domain. We created a problem by putting the polynomial in the denominator, so we fixed the problem by talking about the domain. There's honestly no point in doing the next problem before we go to lunch. So we have two-ish minutes till lunch. We're just gonna take a quick little pause. Now that we're back from lunch, let's go ahead. Oh, did it freeze on the TV? It's gonna catch up. There it goes. All right, so adding functions and determining domains. So we're still doing what we did before lunch, which is combining these functions together. It's just that now this time, when we look at the two functions, there is going to be some restrictions right away. If we have our green function and we have our blue function, f and g, and we're gonna add them together, before we do that, we need to make sure we know the restrictions. Since both of these are square roots, what was the restriction we used for square roots? The radicand is greater than or equal to 0. So we need to take both radicands, x plus 3 greater or equal to 0, and x minus 2 greater than or equal to 0, and know what number that the x values need to be greater than for both of these problems. So for the green one, we need to make sure that x is always bigger than or equal to -3. And for the purple one, we need to make sure that it's always bigger than 2. So keep that in mind for whenever we do the final domain. And I know it's not written in interval notation just yet. We'll do our final one in interval notation. If we take these two functions and we add them together, so f plus g of x means that we are just taking the functions and we're adding them together. So we will have our f function, x plus 3, and we will add our g function, x minus 2. Now we think back to when we learned about radicals. You can only combine radicals together if they have the same radicand. So like, do these have the same radicand? The stuff underneath the square root? They're not the same, yeah? That's full stop where we stop. That's as simplified as we can get this. So while that was not very complicated because we're just adding them together, talking about the domain is going to be a little bit more complicated. If we draw a number line for this one, I know I have the number -3 and I have the number 2 that's important for my equations. Sorry. So for the first one, for the green one, we know that x has to be bigger than or equal to -3. But then for the purple one, we know that it needs to be bigger than or equal to 2. So do you see how now these restrictions are overlapping a little bit? When you're combining functions, the domain of your combined function is the intersection of those two intervals. So where do both colors exist on my number line? Where do they start both existing? At 2. Where do they stop both existing? Infinity. So my domain for this one is from 2 to infinity. Even though the first one said I could use all the way back from -3, the second one says it has to be bigger than 2. So you have to make sure you're looking at where they would overlap, not where they exist individually, but where they overlap. And that's combining functions. How do we feel about combining functions? Good. Let's start composing them. This is what I think composing functions is really fun. So again, you have to pretend like you like it, even if you hate it, because it's one of my favorites. We're working with composite functions. Composite functions is when you take one function and plug it into another function. So instead of just plugging in numbers, we're going to be plugging in entire functions. So it is a double function machine. The composition function, or the symbols that we use for composition, is f of g of x. Don't say fog. If it's backwards, don't say goff. I hate that. That's such a pet peeve for me. This is pronounced f of g of x. These are both equivalent. They mean that you are putting the g function inside the f function. Notice the g function is inside the f function. So if I were highlighting this, we would say like maybe we have a purple function inside a green function, which means we're going to plug the purple one into the green one. That's what f of g of x is telling me. And I find it easier to work with the one where the g is straight up inside the f as opposed to the composed symbol. So that's the one you're going to see the most from me, but they mean the same thing. When we're talking about the domains of these composite functions, the domain of this composite function is going to be in the domain of g, which is the inside function, has to be a part of the inside function, and a part of the entire function, the final function is what I'm going to call that. So it has to be a part of the inside and a part of the final to be in the intersection for this particular domain. But when we're doing function notation for this, what's going to happen is since g was on the inside, this is the bubble for g, and this is the bubble for f. I'm going to take some value and I'm going to plug it into g. G is going to do something to it, and you're going to have an output. I immediately take that output and I plug the output as an input into f. So you're plugging inputs or outputs as inputs to double up on composition. Okay, here let's see what this might look like. So if I'm doing for these two functions, we'll color these as well. We'll have f of x be green and g of x be purple. It's just easier to see these as two separate things right now while we're learning. But if we're doing f of g of x, we are doing f of g of x, which is a whole lot of colors at a whole lot of times. F of g of x. Oh, sorry, we should always check domains before we start. What kind of function is f? Linear. What kind of function is g? Are there any restrictions for linear or quadratic? No, so this one has a domain of negative infinity to infinity, and this one has a domain of negative infinity to infinity. That's good. No starting restriction, easy peasy. When we start to compose them, we're going to slowly take the f function and plug into it the entire g function. Okay, notice I just replaced g of x with its equation, yes? But now since that is inside of the parentheses for f, that is telling me to plug all of that purple stuff in the green function everywhere there was an x. So what this will start to look like is the following. The green function is 3 times x minus 4. But the thing I'm plugging in here is x squared minus 2x plus 6. So instead of plugging in a number, I'm plugging in the entire function g. Once you've done this, once you've done the plugging in, all we have to do is simplify. So since we have a 3 in front of a bunch of parentheses, we're going to distribute. We'd have 3x squared minus 6x plus 18, and then minus 4. Thank you. Last step to simplify, we have 3x squared minus 6x, this is plus 14. And that is the composed f of g of x. We took g, we plugged it into f. As a bonus, what kind of function did we create at the end? Quadratic. Is there any restriction to quadratic? No. So since there was no restriction to the inside function and no restriction to the final function, the domain is all real numbers. What if we did this the opposite direction? Do you see how this says f of g? So we took g, put it in f. Part B says g of f. You see how the letters switched order? You switch the order in which you compose them. This time, g is going to be on the outside, and f is going to be on the inside. The order matters. This is g of f of x. So inside the g function, I'm going to plug in the entire f function, 3x minus 4. So g of 3x minus 4 tells me to plug in 3x minus 4 anywhere there was a g, or sorry, an x, you're welcome, in the g function. So it'll look like this. We have equals. Something squared minus 2 times something plus 6. The something is the f function. So again, we see we're taking the f function, plugging it into the g function. After you plug it in, all we have to do is simplify, which in this case is not super simple. We do need to multiply all of this stuff out. The first part is a FOIL question. Don't just try to distribute that 2. This is FOIL. This would be 9x squared minus 12x minus 12x plus 16. If you're like, whoa, what? How did that happen? I did this. 3x minus 4 times 3x minus 4. I FOILed. The second part, I just need to distribute that negative 2, which would make negative 6x and positive 8, and then drop down the 6. Once all parentheses are gone, we combine like terms. We end up with 9x squared minus 30x plus 30. What kind of equation did we end with here? Is there any restriction on quadratic? And there was no restriction on the one I plugged in. The inside function was linear, no restriction. I'm sure there's questions comparing these two. Can we ask a couple questions before we move on? A moment for you to focus in on that we might make a mistake on. Totally right here. A lot of people will just try to distribute this 2, the squared, into both pieces. That's not what this is. Remember, this is a FOIL. Double distribute. I'm sorry, the door is shutting and I didn't hear you. Correct, yes. So the one that it's right in front of, so we would go boop and boop. Is that what you're talking about?
Yeah, and then you just broke those two apart, right?
Are you talking about right here?
Yeah, I just broke them apart.
I wrote it apart so you could see what I was foiling in my head.
Oh, okay.
Yeah. Which might be helpful while we're still like foiling in our head. Yes. Any other questions? What if it says like C? What's the difference between B and C? There's a 1 right here as opposed to an X. So when I rewrite this one with one function tucked inside the other function, this is actually going to be g of f of 1. Meaning I'm not plugging in an x into the f function this time. I'm plugging in the number 1. So if we do this piece by piece, I want to take the f function and put a 1 in it, which means I'm going to write 3 times something minus 4. That something is the number 1. Yeah, let's look, compare to what we did before. What's different in my first step? Do you see the difference? The second one says f of x on the inside, so I put f of x with x's plugged in. The other one says f of 1, so I put a 1 plugged in. Okay, let's make this a little bit easier on ourselves. Let's just go ahead and simplify what f of 1 would be. What is 3 times 1? And then minus 4. So this part equals negative 1. That's the output I get when the input is 1 for f. But since it's already inside those parentheses, g of negative 1 just tells me to plug negative 1 into the g function. So I'm just going to do exactly that. We're going to do, wrong color, -1 squared minus 2 times -1 plus 6. -1 squared is 1. -2 times -1 is +2. And then I have +6. And voila. That's 9. So the difference here, if there is a number that you're plugging in a number. If it's an equation you're plugging in, you should have an equation answer. Comments, concerns, questions? No? So we kind of talked about this at the beginning, and we checked both of these A and B to see the domain of the inside function and the domain of the final function. But what happens when we do have a restriction to begin with? So this is going to be an example that you look at when you're confused about the restrictions. This one might be really helpful. Remember that again, if x is not in the domain of G, it cannot be in the domain of the composition. And it has to be in the domain of the composed function. So we're again looking at the inside, that's a highlighter, inside and final. Okay, inside and final. This doesn't mean nothing yet until I show an example where it means something. Inside and final. All right, we're just going to do both f of g of x and g of f of x for this problem. Oh, no, we're finding the domain. It didn't switch it. Okay, find f of g of x and the domain of f of g of x. Woo! Let's highlight and make this make more sense. Here's f. F is on the outside. Here's g. G is on the inside. We're composing something, so my spidey senses tell me I need to make sure I know what the composition or the domain of the inside and the final is. G is on the inside. What number can I not use in the domain of G? What is x not allowed to be equal to? 0. Just for good measure, because it's nice to know, what is f not allowed to be equal to? 1. That's extra info. We don't need it because G's on the inside. So let's compose these. If we're doing f of g of x, we're doing f of g of x, which means take the f function and put the g1 inside of it. So anywhere there was an x in the f function, you put that whole purple thing. So here I go. We have 2 over x minus 1, but x is the purple function 3 over x. Great question. Thank you for asking. This is the purple, yeah? Purple's on the inside. So I'm going to take the green function, but anywhere there was an x, I'm going to put the purple thing. So I wrote down 2 over x minus 1, but the x is the purple function. It's no longer simple x, it's the entire. What do you mean?
That's what confused me when you wrote f times 3 of x.
Oh, remember, that's not times. This tells me to plug it in.
Yeah.
F of 3 over x means I'm going to take, because oh, I see the question. Okay, this normally says f of x, right? Mm-hmm. So here's f of x. So whatever's plugged in there, even if it's an entire crazy looking function, you plug it in where the x goes. Better? Yeah. Okay, so the problem with this is that now we need to simplify this function, and we all panic when there's fractions. We're not going to panic when there's a fraction. What we're going to do is we're going to multiply the top and the bottom by the denominator in the denominator. Maybe you want to write that down. What's the denominator of the denominator? X. I'm going to multiply the top and bottom by that denominator, whatever the denominator in the denominator is. When I do that, my function becomes 2x on the top. It becomes 3x over x minus x, because this like distributes, right? Boop and boop. What happens to 3x over x? The x's cancel. So much so I'm just going to do this. Boom, the x is canceled. That's why we multiply by the denominator in the denominator. There's nothing else I can simplify here. So this is f of g of x. The problem is we have a restricted domain. I know we have a restricted domain because we started with the inside function having a domain, and we have now the final function having a restriction on the domain. What number is this function not allowed to be equal to that I have a box over? To 3. So for this one, x cannot equal 3. But we also have to include the domain of the inside. What was the domain of the inside? The purple, what was the restriction for purple? 0. So my domain is it cannot be 3 and it cannot be 0 because the inside function caused me to say not 0. The final function told me to say not 3. Inside and final. If we were writing this in interval notation, which I will ask for you to do, the interval notation here, the final actual domain, would be from -infinity to 0, 0 to 3, or 3 to infinity. But again, if you want to write this down, this was the domain of the final. This was the domain of the inside. Final and inside are the ones that matter. Outside doesn't really matter. Just final and inside.